Hi, and welcome back to The Joy of Ray Tracing. I'm your host, Eric, and in this video series, we'll be making several ray tracers from scratch. So today marks the first episode of Chapter 1, and I'm really excited because we're going to start creating our first ray tracer from scratch. On the last chapter, Chapter 0, we took a look at how to set up a productive coding environment. And we also learned the basics of the JavaScript programming language, which we'll be using to create our first ray tracers. And towards the end of Chapter 0, we took a look at how to set up an account on GitHub, and we created our very first repositories on GitHub so that we can easily store our source code as well as share our projects and demos that we'll be making here on this series with others online. And finally, we took a look at a really cool feature which is inside our code editor, VS Code, and that is called Live Server. And that allows us to easily run our code as well as see the changes that we make to our code immediately. And not only that, you can connect all the devices on your Wi-Fi network up to the Live Server and then see the changes immediately on those devices as well. So that's really cool. So on today's episode, which is the first episode of Chapter 1, we're actually going to start creating our very first ray tracer. So I'm really excited to get started on our journey. So let's take a look at what we're going to do today. This is the section I like to call Today's To-Dos. First, we'll briefly discuss what even is ray tracing and the different types of ray tracers that you can make. So there's CPU ray tracers, there's GPU software ray tracers, and nowadays GPU hardware ray tracers, and we'll briefly discuss each of those. And then we'll discuss what kind of ray tracer we're going to build first, and what the goals of this first ray tracer will be. We'll start by creating a really simple HTML web page shell that will hold all of our future ray tracing projects. We'll then use the JavaScript programming language to create a drawing canvas on our simple web page, and that will allow us to draw our very first colored pixel on the screen. And getting that very first pixel drawn on the screen is kind of like a rite of passage for us graphics programmers. Once we successfully have the first pixel on the screen, we can create a loop that loops over all the pixels on the screen and then sets each of them to whatever color we want. And finally today we'll take a look at 2D screen coordinates, which are simply the x-coordinate and the y-coordinate of your screen. And we'll play around with this idea of screen coordinates by changing each pixel's color depending on where it is located on the screen. So let's get started. All right, first let's talk about what ray tracing is and why we would want to use this technique over other techniques that are available to us. So if I just do a simple search for ray tracing on the web, nowadays you might get some hits related to NVIDIA's new RTX lineup of video cards that provide support for real-time ray tracing. But when we say ray tracing in the general sense, in the classical sense, then if you go to a typical article on ray tracing, then you might come across some cool images. This is one of my favorites here. And if you scroll down this Wikipedia article, you'll see some more realistic images. Here's one of the best ones. And so this image, even though it looks like a photograph, was created one pixel at a time using ray tracing. So it's pretty amazing what you can do with the technique. But in a nutshell, a ray tracer is a piece of software that generates a realistic image on your computer. And the technique of ray tracing involves shooting out rays from our camera, which we can place anywhere in the scene. So you start at the camera, and for every pixel on the screen, you fire out a ray that goes through that pixel, and then all those rays go out into the world that we define, so we can place any objects we want out in the world, and we can light it however we want. And then those initial camera rays interact with the scene and report back what they found for that pixel. So if you follow this ray, for instance, on the top, it goes through this pixel out into the scene, it hits the sphere, it then sees if it can see the light source, which it can, it's not in shadow, and it reports back a bright orange color. And so if you follow it back here to where the pixel is, it turns the pixel orange. And so basically that's ray tracing. Now there's a whole lot more that you can do with the technique of ray tracing, but in a nutshell, that's what you're doing. You're just firing out rays from the camera, having those rays interact with the world, and report back what color they see. That's basically what happens inside of a ray tracer. And as we get farther into this series, I'll discuss more in detail how all of this works. And I'll show you how to actually implement this on our computer. And so it'll generate a realistic image for us. So why would we want to use ray tracing versus the other style of rendering, which is rasterization? So I would like to show you this slide that I think pretty well shows the differences between rasterization and ray tracing. So we have two different renderings here of the same scene. We have a teapot, a teacup, a plate, and a spoon, all sitting on a table with a wall with a little pattern on it in the background. Now they both have the same resolution, so the same number of pixels, and they're both shot from the same angle, and they have the same geometry in the scene. But one of them looks way more real than the other. So why is that? Well, this is the traditional rasterized way of doing things. And with rasterization, this is what you get out of the box. So if you just define your scene and say, I want a teapot here, you would have to provide the 3D model of it, of course, but let's say I want the teapot here, I want a table, and then I want the teacup and spoon on top of the plate and the wall in the background. And I want the light source up here somewhere in the ceiling. And basically this is what you would get if you didn't do any extra work with rasterization. So certain parts of this scene look okay, like the reflection here looks kind of cool, and the texture on the teacup looks nice, but it's a little flat, isn't it? It seems to be missing that special something. And the first thing that I notice is that it's missing shadows. And so there's no dark spot under this teapot, and there's no dark spot under the plate either. And if you don't have shadows, it almost makes the objects look like they're floating. So this teapot could be like floating over the table, depending on our camera angle, and we wouldn't know it. Same with the plate here. This could be just floating in front of the camera, and the table could be really far away. We don't know how big this is compared to the table in the background because there's no shadows, and shadows provide those important depth cues, like how far something is away from us, as well as how the objects are related to each other, if they're sitting on top of each other, or they're floating in the air, or they're underneath something else. So now let's contrast that with this image on the right, which is the same scene, but now it's ray traced. And so we now can see shadows under the teapot as well as the plate right here. And that gives us an important depth cue as to how those objects are related to the other objects. And so now we can say that this plate is definitely sitting on this table because it's casting a little shadow right here underneath it. As well as this teapot, you can tell it's sitting on the table because of the dark shadow underneath. It almost looks like a photograph, especially this teacup and the spoon and the plate. That could pass for a real photograph. And also immediately what I can see here is that there's a reflection of the environment or the room surrounding this whole scene. And so you can actually see where the light source is coming from. And also the spoon is correctly reflecting its environment, whereas this one kind of looks lifeless and dull. Now, this comparison doesn't really do rasterization justice because modern techniques in rasterization have come a long way over the years. And if you've seen or played any recent AAA 3D games, you know that the graphics can be very realistic on those. And so this comparison is almost unfair to rasterization in terms of what it can do now. But there's a big caveat there in that if you want to include all these realistic effects from ray tracing back in your rasterized version, you have to do a whole lot of work. And you have to have a lot of knowledge about graphics programming to be able to pull something like that off. So yes, you could add shadows back into this, and you could add reflections using like a cube map or something like that. But you have to know about those techniques, and those techniques are approximations to what you get in ray tracing. And essentially they're kind of like hacks. So you constantly have to monitor and tweak those hacks to get them to look realistic. So if you decide to use rasterization to render your images, you only get these basics out of the box. So it'll put the objects up there on screen, but it won't light them or make reflections or shadows or anything like that. If you want any of those elements, you have to retroactively add them back in, and you have to know how to implement those sometimes complex graphics techniques. Now, if you choose ray tracing, you get all this visual reality out of the box. And so once you cast your ray through the pixel, you just reflect it off the objects, and it continues to bounce around the scene, and then it just reports back what color it sees. And so you color the pixel whatever color that may be. So for instance, if we start up here in the left-hand corner and I fire a ray through this pixel, it's going to hit the wall, and then it asks, can I see the light source from here, or am I in shadow? And so it fires another ray towards the light, and yes, it can see the light, and so therefore it comes back a bright white color. And so we do that for every pixel until we get to here, and then our first pixel hits this teapot spout, and it says, well, this is a reflective surface, so I'm going to reflect. And so that little ray reflects, and it may hit something else, may hit the light, depending on how we're looking at the object, and then it reports back what it found. And then you get down here maybe where my mouse pointer is. So let's say we're all the way down here now, and we fire a ray through this pixel right here, and it says, okay, I hit the table, so that's a brown color, but can I see the light source from here? So it fires a ray towards the light source, but it hits the plate on its way to the light, and it goes, whoops, I hit something, so I'm in shadow, and then therefore it leaves this a little darker. And so you get all the shadows and reflections and the realistic lighting all with the same technique. And so basically you get those realistic effects for free by doing the same ray tracing process. So you may be wondering, why go the rasterization route when we could just go the ray tracing route and get all this realism for free and not have to do any hacks to add them back in to the rasterized image? Well, the reason is speed. This type of rendering, rasterization, has been supported by every graphics card that's ever been made. And so graphics cards are designed to take any scene geometry that you want, which is usually triangles, a big list of triangles, and it quickly puts those up on the screen, and it does so at 60 times a second. So therefore you can have interactive applications or games that run at real-time frame rates, but you pay the cost and that you have to add the realistic effects back in if you want to approach the fidelity of ray tracing. Now, ray tracing, on the other hand, is traditionally very slow and computationally very expensive. And so you can imagine we fire one ray through this pixel, then we go on to the next pixel, then we go on to the next pixel, then we go on to the next pixel, and all the way down till we get to the bottom right-hand corner of the screen. And on a typical 1080p display, that's over 2 million rays that we have to fire out. And those are just the first rays. Then all those 2 million rays have to interact with the scene and create more rays that fire out towards the light or reflect off of a shiny surface or possibly refract through glass or transparent objects. And so you can start to see the computational cost associated with ray tracing. So having something like this run in real time at 60 frames per second was unthinkable a couple of decades ago. But nowadays, with the new NVIDIA lineup of RTX ray tracing cards, they're trying to change that, and that you can have real-time ray tracing. So eventually, I think we'll leave rasterization behind and move towards all ray tracing and have that run at 60 frames per second. But the hardware is not quite there yet, and it's very expensive also. So a lot of people don't have access to these fancy graphics cards that can do this kind of ray tracing in real time. But I believe we're going to move towards this style of rendering when the hardware gets faster and cheaper in the near future. And one more thing before we leave this image is that once you render something like this on your computer, it's hard to go back to this because you miss all those realistic effects that you get for free with ray tracing. Let's take a look at one more comparison. And so this image shows again what you get out of the box with rasterization versus what you can achieve with ray tracing. On the left side, we have a technique using direct lighting, and that means that anything that's in the scene that can see the light source directly, it gets lit up. Now this ceiling is white, but it's showing you that since everything's just being lit by how it can see the light, you don't actually get any light up here because the ceiling can't see into itself. That light source is up in the ceiling itself, and so the ceiling can't look backwards into the light. This technique doesn't account for light that's bounced around the room, and therefore the ceiling is left in the dark. Now, as I mentioned before, you can add shadows back in with a technique called shadow mapping. And so we can see that here. We have some shadows, and that does help a lot with the visual depth cues in the scene. So we can tell that these spheres are sitting on the ground because of their shadows. But still, we're missing those reflections and bounced lighting that we usually see in real life. And so this scene, again, looks a little cold and uninviting, like I wouldn't want to go in there and visit this scene, right? So now look on the right side, and immediately we notice all the light that has been captured in this image that was left out of this image. So now the first thing I notice is that we have the ceiling color back, and so the ceiling is being lit by bounced lighting around the room. So the light comes here, it bounces off the floor and then back under the ceiling, and then we get that nice bounced lighting effect. Also, there's some color bleeding between the red wall and the white ceiling. You can see it right here. And then a green color bleeding on the white ceiling over here in this corner. That's a very subtle effect. You wouldn't usually notice that in real life or in a photograph, but in real life, it really does look like that. So if you look into a corner of a room where one wall is a bright color like red or orange or green, and then the other wall is just a plain white, you'll get that color bleeding effect on the white wall. So the next time you're out and about, see if you can spot that in real life. And once you see it, you can't unsee it. So it's one of those things where we just take it for granted, but if you take it away, something doesn't seem right about the image. And that's what we're missing over here. We're missing that color bleeding and the bounce lighting that we would normally get with a photograph or looking into a real room. The next difference is between the shadows. So over here with the shadow mapping technique, if you just add shadow mapping to your rasterized image, even though it's really fast, it goes at 60 frames per second, it makes hard shadows unless you manually blur them out at the edges, at the penumbras of the shadows. But here, just by ray tracing, you get these beautiful soft shadows on the floor and on the wall, basically for free, just by doing ray tracing. And I should mention before we go on that this is using a technique called path tracing. And path tracing is an evolution of classical ray tracing. And so we will get to techniques like this in this video series, but it'll be a little later. We're going to start with classic ray tracing first and just get something up on the screen that has reflections and shadows. But then in order to get these color bleeding effects and these soft shadows with an area light source, you have to use path tracing for that. But as we'll see, path tracing is a natural extension of ray tracing. And so once we learn how to do ray tracing, path tracing is just the next natural step. One final thing is, if you notice here, we have a reddish sphere. And then over here, they've made it transparent to show off the refracted light rays and how light gets bent as it enters the glass sphere and exits out the other side. And also we get these cool caustics on the floor. So if you have a bright light source, such as this light purple area light on the red wall, it can come through the sphere and then get refracted and then refract again on the other side of the sphere. And then that light is tightly focused right on the floor right here. And so it creates a hot spot. And so again, you get these realistic effects that are, you might not notice them in real life, but if you take those away, then it looks sort of cold and bland. Now again, this is not doing rasterization justice, because just like the shadows were added back in, you can actually add in some of this lighting to these walls back here. So if you wanted these walls to look more colorful and realistic, you could actually perform ray tracing and bake what's known as a light map. And then it's basically a texture with all that color information in it. And then you just apply the texture to these walls and the ceiling and the floor. And then you get the bounced lighting in your rasterized scene. But if anything changes in the scene, so if you move the light source or if you move an object, then all that information is outdated. But in the ray tracing version, if you move this light or make it smaller or move these spheres around, it'll immediately update the realistic reflections and refractions and caustics and bounce lighting and everything. And if you have this running in real time, it'll do that many times a second, so you won't even notice any delay. But in order to have those elements in your rasterized version, you have to know about all those techniques of shadow mapping and light mapping, or cube mapping if you want to do reflections on a reflective surface. And that requires a lot of graphics knowledge and expertise in how to handle those techniques and putting the realistic elements back into the phony looking rasterized image. Whereas with ray tracing, all those realistic effects just kind of fall out of the technique itself. It's a natural occurrence of using the technique of ray tracing. So that brings me to what type of ray tracer we're going to build first. So typically when I think of ray tracing, and classical ray tracing in particular, I think of images that contain spheres and checkerboards and things like that. And so you've probably seen those in the past. And so my final slide here is a collection of what I think of when I think of ray tracing. So here's that. And so typically when you think about classic historical ray tracing, it usually involves spheres because those are the easiest to intersect rays with, and also some kind of plane or floor with a checkerboard pattern. And so that's the classic style of ray tracing. And although this image here features different shapes that make up the chess pieces, I wanted to include this one as well because I really like the reflections in the chessboard on this image. You can see a reflection of this chess piece here, and that in turn is reflecting the light source. So you get a reflection of a reflection, which is kind of cool. So, and as I mentioned, you kind of get all those cool effects for free just by doing the ray tracing process. And so we'll be able to do this on our ray tracers as well. So one last thing before we start coding today is that I want to briefly discuss the different types of ray tracers that we can build. So historically, ray tracers have been written for the CPU. So typically you would use a language like C or C++, and you would write software that uses only one core of a CPU, and it would just loop over all the pixels and render the image. And so that's what we're going to start off with, although we're going to be using JavaScript instead of C or C++. So we're going to use JavaScript in a way that it'll loop over all the pixels of the screen and then fire out a ray through each of those pixels. And then those rays will interact with the scene and report back the color for that pixel. And then we'll end up with a realistic image. Now, traditionally, CPU rendering like that is very slow. And so although it does produce really nice and realistic images, you might have to wait a second or two before you can see the final image. Now, if you want to speed things up, you can move everything to the GPU. And so typically how you do that is you write what is known as a shader, and that's in a shading language like GLSL or HLSL. And you write your ray tracer in that language and then offload that to the GPU. And then the GPU handles all the pixels all at the same time. So it can send out all those millions of rays in parallel, and then you can get the image back almost immediately. So you can actually get it up to 30 or 60 frames per second. And so towards the end of this video series, that's exactly what we're going to do. We're going to move all this ray tracing and path tracing to the GPU and then write shaders that run on your GPU and that do ray tracing and path tracing in real time, which is really cool because you can fly around your camera in the scene, you can go explore the scene, you can move objects around in the scene, you can change the lighting, move the lights, and it all updates in real time. And so that's really cool. And so we will get to that, but we're going to start out with the more historical, classic CPU style of ray tracing, just to get something up on screen and to learn the basics of ray tracing. And then in more recent times, we have what is known as GPU hardware ray tracing. And so when you see the new video cards coming out from NVIDIA and ATI that say that they support ray tracing, that's what that means. They have dedicated hardware and processors inside those graphics cards that can handle operations for ray tracing so that you can greatly speed up the rendering of your ray traced scenes. Now, having said that, we won't quite go that far with GPU hardware ray tracing because that requires that you and your users have the latest RTX cards that support ray tracing. And as you may well know, those graphics cards are still quite expensive and hard to get. And so my ultimate goal with ray tracing is that you can write it once and then run it everywhere, and you can share it with the maximum amount of people. Because even if they have like a cell phone that has a basic GPU in it, which most cell phones nowadays do, they can run your ray tracers in real time on those cell phones. And so you don't need the latest expensive graphics cards to be able to enjoy ray tracing or to share your ray tracing projects with other people. So that's why we won't quite go that route with the GPU hardware ray tracing, but we will do GPU software ray tracing. So today we're going to start writing our very first ray tracer, and as mentioned, that will be a CPU style historic classic ray tracing program. And so our goals for this first CPU ray tracer will be to be able to render something like this image here in the left corner, or this, or even this. We will be able to do this right here, the reflections, but we won't quite get to these kind of shapes on our very first ray tracer. We'll just stick to a plane and spheres for our first ray tracer. That might seem limiting, but you can, as you can see from these images, you can actually get a lot of different effects and a lot of different moods for your images. So now that we've outlined our goals and the type of ray tracer that we're going to be doing, how about we get started on writing our very first ray tracer? Okay, let's open up Visual Studio Code. And this is where we left off on the last episode. We had just updated our README for our online repository on GitHub. And so since we're starting a brand new project, I want to start from scratch. So we can go ahead and click out of all these files. Now I'm going to start with a clean slate and code everything live here on camera. So one of the first considerations with doing anything related to graphics like ray tracing is what kind of environment you want it to run in. And back when I started ray tracing 7 or 8 years ago, I wanted to be able to run the ray tracer on any device that I happen to be on, whether that be a desktop, laptop, or even a cell phone on the go. And so the platform that I chose and that we will be using on this video series is the web platform, and in particular, the modern browser. All browsers nowadays come with built-in graphics capabilities that we can utilize. And since most every modern device has a browser of some sort, you can be assured that it'll run on the widest variety of devices out there. So since we are using the browser as the platform to run all of our ray tracing, we need some sort of web page to contain all of our ray tracing projects and to be able to display our ray traced images in the browser. So that's what we're going to do now. We're going to create a very simple HTML web page shell that will be like a container for our ray tracing code and our projects. And once we write this little web page shell, we'll be able to use that as a template for our future projects. And so we can literally copy and paste it from one project to the next. So let's create that little web page shell now. So click on Ray Tracing Projects and click on it one more time just to make sure that you're in that folder. And let's add a new HTML file called Pixel Loop. So how you do that is you click this new file button right here, and I'll name this pixel loop.html. Make sure you have the HTML extension. Hit enter. And now that created a blank HTML code file. So now I'm just going to add the elements to our web page that we need in order to contain all of the ray tracing code and to be able to display the final image on the web page itself. Now, although I'm going to do everything on the screen here, I'm going to go a little faster than I did in Chapter 0. So if you, for some reason, missed Chapter 0 and you're just joining us now, and this is going a little too fast for you, or you're not quite sure what all these things are doing, and you're not familiar with web development in general, then I highly recommend that you go back and watch some of the videos in Chapter 0, particularly the ones on HTML and JavaScript and CSS. And so those will get you up to speed with what we're doing now. But these are very basic elements of web development. And what I'm doing today is very basic stuff. We're never going to get really deep into web development. We're just using it as a basis or a platform to build our ray tracer on top of. So the first thing we need in any HTML file is the document type. And you do that by Shift >, and then it comes up right away. You can click on doc type. That'll tell the browser what kind of document it's about to read, and it says HTML. Hit enter, and next we'll have the HTML tag. So Shift <, and then type HTML, and it'll come up there. Click on there, and then Shift > will close it up for you, and then hit enter. Now we're going to put all of our HTML code inside these opening and closing HTML tags. And next we have a head element. So Shift <, and then start typing head, and it'll come up. Shift <, to close it up, and then hit enter to put that on its own line. So now we have an opening tag and a closing tag for the head element. Inside that element, we're going to add a title element. So opening tag is Shift <, and then let's do a title element. So type T, and it should come up, title, Shift <, to close it up. And on this one, you don't need to press enter. We can just have this all on one line. So give it a space here, and let's call this pixel loop. Go to the end of the line and hit enter. And we're going to leave a space here for something that I'm going to add in just a moment when we add the CSS file. So let's go here right after the head closing tag and hit enter a couple of times. And let's do a body element now. So the opening tag is Shift <, and then type body, and it'll come up. Click there, and then Shift <, to close it automatically. And this one we do want to hit enter to put it on its own line. So in order to draw anything in the browser or a web page, you have to have a canvas. And so we're going to create a simple canvas element right here in the body. And that works just like any other element. You do the opening tag for that element and the matching closing tag for that element. So the opening tag is Shift <, and that's called a left angle bracket, by the way. So I've been saying Shift <, but that's what I'm typing on the keyboard, but it's called a left angle bracket. And the other one is called a right angle bracket. So left angle bracket, and then type canvas, and it should come up. And now Shift <, or right angle bracket, and that'll close it up. And give it a space there so you can clearly see where the opening tag starts and ends and where the closing tag starts and ends. And now inside the canvas opening tag, between the S and the right angle bracket, put your cursor right there and then put a space. We're going to give this an ID that we can reference in our JavaScript file later. So let's give it an ID. So type ID, and then you click on ID here, and it'll fill in the code necessary. So it puts an equal sign and a pair of quotation marks. And let's call this my canvas. So that's typically what I do. and I'm using camel case. Remember, we talked about that on the JavaScript episode. So all the names that you choose for variables or components in your project usually start with a lowercase, and then any other words that follow that start with an uppercase letter. So in this case, it's small m for my, and then canvas is the next word, so we begin that with a capital C. So just a real quick recap on that, what I'm doing there with the case style. Okay, then go to the end of the line and hit enter. And we're going to do something very similar, but now we're going to create a paragraph element, and that is denoted with the P opening and closing tags. So to left angle bracket, shift less than sign, type P, and then click there, and then shift greater than sign or right angle bracket to close it up, and give it a space there. And this paragraph element will serve as the output text for the user and for us too, if we want to see what's going on inside the program. So we can just type a temporary message here, but it'll get overwritten when we write something to it later with JavaScript. So we can just put user text info. And then much like we did with the canvas element, we're going to give this paragraph element an ID also. And then that way we can grab that ID inside the JavaScript file and write whatever we want to inside this little paragraph element. And it'll display it on the web page. So click right between the P and the right angle bracket and put a space and type ID. And it'll come up and you can just click there. And let's name this user info. So small u and then capital I for the next word, user info. And that's sticking with the camel case convention of small letter to start, and then every word that follows starts with a capital letter. And then now go to the end of the paragraph element and hit enter a couple of times. And we're going to place another link in here to our JavaScript file. So now let's go ahead and create a CSS file that's going to be linked to right here in this line, this blank line. And then we'll create also a JavaScript file to go along with our project that will be linked to right here in this blank line. And we're going to fill in those lines very soon. So let's create the CSS file first, which is the cascading style sheet file. So over here in the File Explorer, click on the CSS folder, and you can click on it a couple times just to make sure that you're in that folder. And now click the Create New File inside that folder. Usually CSS files have styles or something like that in the name. So let's call this RayTracing styles. And then type .css, and you'll see a little hashtag symbol come up here, which lets you know that it recognizes that that's a CSS file or a style sheet. Now hit enter. So now that created a blank CSS file for us. Oh, and by the way, you can see that there's green U's on these files right here and right here. And you can see there's two notifications over here that two files have changed, and so we've added these two new files. And so those are, the U means untracked by the Git system, but as soon as we upload this to our GitHub repositories, it will start tracking those files and those green U's will go away. So now let's create a really basic style sheet, and this will define how everything looks on the page and how big things are and what color they are and things like that. So recall from the episode on HTML and CSS that we use the CSS language to define these styles for our web page. And so we can just type HTML, comma, body, and then hit enter. And now the curly brace, so on the keyboard it's shift left square bracket, and that should get you a pair of curly braces. And now you can hit enter. These styles that we're about to define will apply to the HTML and body elements in our web page. So let's give our web page a background color first. So type background color and it'll come up. You can just click there. And let's just give it a gray background. So you can scroll down to gray and just click on that. And it fills in a little preview of what that's going to look like, which is nice. And like on previous episodes, we don't want any margins at the edges of the web page itself. So we're going to type margin, click there, and click on 0%. That'll make sure our graphics go to the very edge of the browser window. The next line is for getting rid of the ugly scroll bar on the right. So if you don't have this next line of code that I'm about to add, and if you try to add a little more elements than can be displayed all at once, it'll add this scroll bar on the right and it'll overflow to the bottom of the page. So you'll have to scroll down to see the rest of the web page. So we want everything to be contained on one web page and no scrolling. So we type overflow, click there, and then click on hidden. And so that'll prevent the scroll bar from popping up on the right side of the page. And then now go to after this curly brace here and hit enter a couple times. Now we're going to reference the elements that we had given an ID name to back in the HTML file. So if you recall, we gave the canvas an ID of my canvas. So now we're going to reference that name in this CSS file. And the way you do that is the hashtag. So hashtag my canvas. And that'll grab a reference to this canvas element right here. And then hit enter. And likewise, you do the left curly brace, which is shift left square bracket. And it'll close it up for you and then hit enter. Now this is the element that we're going to be drawing the graphics to. And so I want it to cover the whole entire web page, and I want it to be fixed in place so that it can't be moved around by other elements on the web page. So the way we do that is type position, click on position, and then click on fixed. That'll fix the canvas in one spot and it won't move for the entirety of the program. And likewise, we can give it a background color. Let's give it a different background color than the web page itself. So how about black? We type background color again, click there, and then you can click black. And then as I mentioned, I want the canvas to stretch across the entire web page. I don't want to be able to see anything else underneath it. So let's do width, click there, and click on the percent, but change that to 100%. And likewise do height, click there, click the percent option, and then change that to 100 as well. So now that'll stretch the canvas out to the edges of the browser window. So the width will be 100% and the height will be 100%. And therefore, if we see any gray at all, something's wrong, because we should just see a black background, the canvas that's displayed over the whole web page. There should be no gray background visible. And then much in the same way that we grabbed a reference to my canvas, we can grab a reference to user info as well. So remember that we called this user info, this paragraph element here, and that's where we're going to put the text output. So click to the right of this curly brace here and hit enter a couple times, and then do the hashtag symbol and then user info. Hit enter, and then left curly brace, and it'll close it up for you, and hit enter. And now just like we did here, its position is going to be fixed on the page. I don't want the text moving all over the place. I want it in one spot on the web page. So type position, fixed. And since we have a black background, let's give the text a bright white color so that we can see it. Otherwise, the text will come out black on a black background and you won't be able to see your text. So let's give it a bright color. And the way we do that with text is just color and then type W, and white should come up here. And that way it'll show up on the black background. Now by default, the position that this element will be on the web page is in the top left corner. But for our purposes and for user output, I want it to be on the bottom left corner instead. So what we're going to do is just specify a distance from the bottom and a distance from the left side of the web page, and that'll place it right in the corner on the bottom left. So we type bottom, and then you can click on the percentage again. Let's move it up 2% from the bottom. So the bottom of the page would be like way down here, and then it'll move up 2%, so about right there on the web page. And now we can specify a distance from the left side of the web page. So type left, click there, 0%, and we maybe just do 1% for this. So here's the exact edge of the browser window, let's say, and then it'll move just a little bit over to the right. So it'll be 1% from the left edge. And then with CSS, you can specify what kind of font you want the text to be in. So let's choose a font. So type font, and a bunch of options come up. So let's do font family, and I'll just choose Arial. Most browsers nowadays have Arial or some style that's close to that. I'm going to scroll up so you can see it better. And now let's add one more line. Font size. So type font and then font size should come up. I typically use one of these presets. So let's do extra large just for now, and we can always change that later. Okay, and with that, we're pretty much done with the CSS file. So the nice thing about having an external CSS file like this is that all of our future projects can use it. So we can just link to it from all of our future HTML documents that we write, and it'll use the same style sheet for all those projects as well, and it'll have a similar look from project to project. And we won't have to go in and change anything about this CSS unless we add some new elements, like if we add a button or a slider or something like that. Obviously, we'll have to go back and change the CSS to display that correctly and how we want, and use the styles that we want. But normally, we can just go from project to project, from RayTracer to RayTracer, and just keep using this same CSS file over and over again. So that's nice. Now let's create a JavaScript file that will be in the JS folder. So click on the JS folder icon here. Maybe click on it just one more time just to make sure you're in the JS folder. And now click on New File. And let's name this exactly what we named the HTML file. So pixel loop. But instead of a .html extension, we're going to do .js extension. So .js. And then you can see immediately the little JS icon pops up over here, and it lets you know that it recognizes that file extension. So now hit enter, and that'll create a new file here. So now before we start to type anything into the JS file, let's go back to our HTML file and fill in the lines that link to these files from this HTML file. So first we'll link to the CSS file, and then we do that using the link tag. So go right here underneath the title, and type shift less than sign or left angle bracket. And now we're going to do link. So type L and link should pop up. Click on link and then shift greater than sign or right angle bracket. Now, if you notice, the link didn't have a closing tag, and so it's a special element called an empty element, and it only has one tag. So contrast that with the title element here. So a title has an opening tag and a closing tag. It has the same name twice, but with a little / denoting the closing tag. But a link is a special element, it's an empty element. So all the information goes inside of this tag that you want to link to. So now click between the K and the right angle bracket and type a space. And now the way we reference the file is through an archaic name called href, which stands for hypertext reference. So it's a little bit of an archaic name, but that's what's stuck with us, so we have to use that. So type H, and it should come up right away. So click on href, and it'll fill in the equal sign and the quotes for you. And inside the quotes, we type the path to this file right here. And so this is one of my favorite features about VS Code. And if you've been following along since chapter 0, you know that I love this feature that we're about to see. So all you do is type, so think about where this file is and your folder structure here. We got, RayTracing styles. And so RayTracing styles is inside the CSS folder. So you just type CSS folder, right? And then type the /, which means that it's CSS folder, and watch what happens. See, it gives you all the CSS files inside that folder, and you just click on RayTracing styles, and it populates that link for you. So I just love that feature, and we're about to see it again with the JS file too. So, and we're not quite done with this link element yet. So click between the ending quotation and the right angle bracket and type a space, and now type REL, which means relationship. So REL. So what is the relationship of this file to the HTML document? And so we click on REL. Again, it fills in the equal sign and the quotes, and inside the quotes you tell it that the relationship is a style sheet. That's how it relates back to this HTML page. So type style sheet. So now we're done with the head element. Now let's go inside the body element. And at the last line of the body element here, we're going to include a link to our JS file that we just created. Now, you might think, oh, I'm just going to type link again and I'm going to link it, but it's a little different for CSS versus JavaScript. So with CSS, you do the link element, which is an empty element, and it only has one tag. But with JavaScript, you do a script tag, which is not an empty element. It has an opening and a closing tag. So it's just a little different. But once you've done it 100 times or so, you get kind of used to it. So let's type shift less than sign or left angle bracket and start typing script. And close it with a shift greater than sign or right angle bracket. And that'll close it up for you. And you can type a space if you like. Now this tells the browser that there's going to be some JavaScript in here. You can either type JavaScript right in this, so I could, for instance, I could start just putting some JavaScript in here, like let a = 5. And so it would just execute whatever code I want. But what I really want is for it to go find my pixelloop.js file. And so let's take out that. And all we're going to do is provide a link. And how you do that is go right between the T and the right angle bracket, push space, And then we're going to type the abbreviation for source. So SR, and if you start typing it, it should pop up. So click source, and it'll fill in the equals and the quotes again. Inside the quotes, you're going to put the path, just like you did here with the CSS file. So let's look at this. Pixelloop.js is inside the JS folder. So I'm going to type JS and then a / to denote a folder. And then the magic will happen and it'll populate all the files in that folder for us. So let's type JS folder and then hit / and look at that. Don't you just love it? And we want the pixelloop.js file. And it fills it in for you and we're good to go. So now at this point, we're done with this HTML file. So mainly we're going to be working inside the pixelloop.js file for the next episodes. And so the nice thing about having this document in its own HTML file and the CSS in its own styles file is that you can just keep reusing these as templates and just literally copy and paste from one project to the next and just change the title at the top like this when you start a new project. And so now let's click on pixelloop.js. And this is where the core of our ray tracer will be located. And so let's just to make sure everything's working, let's just open up pixelloop.html in our live server. And so if you remember how to do that, you click on this Go Live button down at the bottom right-hand corner. So click Go Live. And that'll open up your default browser. And then we see all the demos that we've done in the past. So now let's open up Pixelloop, and we should see a black canvas stretched across the whole web page if everything went well, if everything is working. All right, so everything looks like it's working. So we got the black canvas here, and it's stretched across the entire web page. All the width and all the height of the window is taken up by the canvas. That's what we wanted. And then we have our user text output here ready to go, ready to put our message in there that we want. So now let's go into pixelloop.js and let's try changing the text of our little text element at the bottom left corner of the web page. So if you remember from the JavaScript episode, we do that by declaring a variable, and this variable will hold a reference to that text element on our web page. So let's use the keyword let, and let's call it user info, same name, equals, and then we use the document object. So click document and then type the dot character and then start typing get, and we want get element by ID. That's why we gave our element an ID back in the HTML file. So now we're going to put the element ID inside these parentheses. So get element by ID is a function, and all functions have to have parentheses. So opening parentheses and it'll close it, and then it tells you it needs your element ID that's a string. And all strings in JavaScript are enclosed within quotes. So let's type quotation marks, and it can be single or double quotes, it doesn't matter, but I typically use double quotes. Just as long as you're consistent, it doesn't matter. And then let's go back and see what we called it. So user info is the ID that we called it. So let's type that inside the quotation marks. User info, capital I, sticking with the camel case convention. And then it's not a requirement, but all JavaScript lines should end with a semicolon. And so I do like putting semicolons at the end of JavaScript statements. So add a semicolon there. Now, your programs will work without semicolons, but you can run into trouble if you don't put those in there, because sometimes the interpreter can be confused by spacing of your code lines if you don't have semicolons marking the end of those code lines. So now user info contains a reference to this element right here, user info, that's a paragraph element, and a paragraph element displays text in the browser. So we can now change the text to output whatever we want to show to the user. So, and in JavaScript, you do that by calling the variable, so user info. We use the dot operator, and then we want the inner HTML property. So inner HTML, and that's a property that you can set that will display any text that you want. Now all text is in quotations, remember, so we have to say equals and then put quotation marks, and I use the double quotation marks again. Again, it doesn't matter if you use single or double, just be consistent from line to line. And then let's put hello from the JS file. And then again, we like to end our statements with semicolons in JavaScript. It's not a requirement, but I recommend it. So now let's go back into our HTML file and see if that worked. Look at that. Hello from the JS file. So everything is working how we expected. So our CSS is displaying the canvas correctly, and it's filling the entire window with the canvas. We have our title here called Pixel Loop that we named the document. And then finally, it's reading from the JS file, and from the JavaScript file, we can interact with this web page. So we can change the text, we can change the color, we can change the resolution of the canvas, we can draw to the canvas as we're about to do. So once you have that link between your HTML and your JS file, you can do lots of stuff inside the JS file that will affect your HTML document. So now, just like we got a reference to our paragraph element with user info document.getElementById, let's do the same for the canvas element. So as you recall, we have a canvas element and its ID is my canvas. So let's get that by ID also. So hit enter after this line, maybe a couple times just to give it some space, and then create a new variable called canvas. And we're going to use the same pattern. So document, and then dot get element by ID. And now it's a function, so it needs parentheses. And it takes a string inside of the parentheses in quotes. So let's put some quotes. So shift quotes. And if you do the opening quotes, that fills in the closing quotes for you. And then now let's use the name that we gave it. So my canvas with capital C, remember. So, and that's a statement. So we end that with a semicolon. Now that we have a canvas element, we need to get a drawing context so it's able to actually draw graphics to our canvas on our web page. So we get the context by let context. Now we're going to call the canvas. So canvas. And then we use the function get context. For some reason that doesn't get populated in this list here, but just type capital C context. And then it's a function again, so we need parentheses. And now it kind of gives you some info, and it says the first option is 2D. You can do other options like WebGL and WebGL2 and things like that, but let's just do 2D for now. So, and this is a string itself, so it needs quotations again, and then just type 2D. And that was a statement, so we end that with a semicolon. And now we have a drawing context, so we can actually start issuing drawing commands. So before we start drawing, let's set the resolution of our canvas first. And so that simply means how many pixels wide you want the canvas to be and how many pixels tall you want the canvas to be. So we specify that by calling the canvas element dot and then its width property. And then we can set that here in JavaScript. So type equals, and we want the canvas width to be the same resolution as the browser resolution. So how you do that is you just call the window, which means the browser window. So window dot, and you think it would be width, but actually it's inner width because the browser display has certain components on it, like the browser Chrome and the menus and the address bar and things like that. So it wants to know if you want to include all that as well, but we don't really want all that. We just want the inner part of the window, but make it as wide as possible, but don't go into the menu or don't go into the address bar. So window inner width, and it'll pop up here. You can click there, and that's a statement, so semicolon to end it. And now our canvas width will be whatever the browser width is, and we don't know that ahead of time, so that's why this is helpful, because it'll set it to whatever the user's device is set for the browser display. So now let's do the same with the height. So canvas dot height equals window, and likewise it's inner height, because we don't want to include stuff like the address bar and things like that. And then that is also a statement, so, and that with a semicolon. So now let's hit enter a couple times, and let's draw our first colored pixel to our screens. So this is the moment of truth. So call the drawing context, this right here that we got a moment ago. So context dot fill style, and this specifies what color you want to fill the rectangle with. So we're going to draw a really tiny rectangle that's going to act like a pixel right in the middle of the screen. So let's set it to a bright color, because remember we have a black background so on the canvas, so let's set it to like a bright white color. So, and it's a string property, this fill style, so we need quotes for all strings, and let's just type white. The browser will recognize this. Later on, we're going to change this to actual RGB values, so red, green, and blue channel. But for now, we can just put a keyword in there, white, and the browser will know to set the RGB to 255, 255, 255. So it knows what to do with that. So now end that with a semicolon, because that's a statement. And let's draw a little rectangle right in the middle. So if we want the middle of the screen, that would be half of this canvas width. So canvas width divided by 2. So let's try that. So context again. And now we use the fill rectangle function, or fill rect. You type fill rect, but that means fill rectangle. So, and then it's a function, so it needs parentheses. And now Visual Studio Code comes to our aid and reminds us what it needs as parameters inside these parentheses. So X means how far you want it left or right. So 0 would be way over here, and canvas width would be way over here. And then Y is how high you want it to be drawn on the screen. So Y0 is way up here, and Y canvas height is way down here. Remember, it goes from 0, 0 in this corner to canvas width, canvas height down in the right corner. So Y goes up as you go down on the web page. It's a little counterintuitive, but that's how it works. So just know that 0, 0 is up here in the left-hand corner. We'll take a look at that in a minute. I have a little diagram for that. So fill rectangle takes the X first. So let's do it in the middle. So canvas width divided by 2. And then all of the parameters are separated by commas. So type comma. And now let's do the same for the height. So canvas height divided by 2. Height, enter, divided by 2, comma. And now it needs how wide you want the rectangle to be and how high you want the rectangle to be. So let's make it like a true pixel. So it's only going to be 1 unit in width and 1 unit in height. So 1, comma, 1. And now that was a statement in JavaScript, so we end that with a semicolon as well. All right, so now let's go check our web page and see if we have a little white pixel in the middle of the screen. I see it. There it is. You see where my mouse is? It's very tiny. It's hard to see, but it's there indeed. Just in case you can't see it on the YouTube video, I'm going to make it just a little bigger to prove that it's there. So let's make it 4 by 4. So now it's 4 wide and 4 high. And you definitely should be able to see that. So now we have our first pixel in the middle of the screen. So that might not seem like a lot, but once you have the ability to put a pixel on the screen like this, and then once you are able to loop over all the pixels and then set them to a color, you're good to go so far as ray tracing is concerned. And so this first task of getting a single pixel on the screen is actually considered a rite of passage for graphics programmers. And so you should feel proud if you got this far. Let's keep it big so that we can see it on the YouTube video, but I'll put it back down later when we're looping over the pixels. So let's change it to a different color now. So how about yellow? And you can type, again, you can type the keyword yellow and the browser will know how to convert that to RGB values. So let's go check that out. And there it is, yellow pixel. I always like to try this one, magenta. It's a bright pink purple color. That's pretty cool. All right. So if I set it back down to 1 now, can we still see that? I barely see it. It's right there. So the white was the best color for showing up on the canvas here. But let's just leave it magenta for now, because we're going to take this pixel drawing to the next level now. So in every CPU style ray tracer, you need to be able to loop over every single pixel on your device. And so to get practice with this, let's try looping over all the pixels from left to right on a single row. So to help us visualize what we're about to do, I have an image that shows some sample screen coordinates. So let's take a look at that. So your monitor or your screen is divided up into little regions like this called pixels, and each pixel has a location on the screen, and its location is denoted by 2 numbers. An X location and a Y location. And so the X comes first, and then it's usually a comma, and then the Y location is second. And so if we look at the top left corner, and this applies to anything. So this corner right here, and if we go on our web page, it means this pixel right there, that very top left pixel. So that is denoted with zeros for x and y. And recall that in most math systems, the x-coordinate is the horizontal or left to right coordinate, and the y-coordinate goes up and down. And so that's the case here. But since we start at the top left, then the y-coordinate actually goes up as you move down. So it's a little backwards from how you learned in math class, where the y-coordinate usually goes up. So, but we'll fix that at a later date. We're going to actually flip it around so that it'll reflect like a graph. So you'll have x from left and right, and it goes positive as it goes to the right, and then y will go up as positive will go up and negative will go down. So we'll fix that at a later date. But for now, for today's episode, we're just going to deal with the numbers how they are presented in the browser and most image display devices. So this pixel here is 0, 0, and if we follow it to the right, the x increases by one number each pixel. So you can see 0 for the x coordinate, which is the first one. Then it becomes a 1, so 1, and then 2, 3, 4, 5, 6, 7, 8, 9. Now this one stops at 9, but in reality, if you have a 1080p display, that means 1920 by 1080. So 1920 pixels. So this number would go up all the way to 1919. So because remember, it starts at 0, so it's one less than you think. But anyway, this is just like a sample image of coordinates that you can wrap your head around, and so we can get used to identifying pixels by their screen coordinates. So let's try this first. Let's see if we can light up the pixels from the top left-hand corner, which is 0, 0 in our browser window, and then go all the way across until we get to the maximum inner width of the window. So let's create a loop that increments the x value as we go from left to right, and see if we can make the pixels go across a single row. So back in the JavaScript file, we'll create a for loop in JavaScript. And so we're going to use the keyword for, and then opening parentheses. And now we declare a variable that will be the iterator for the loop. So on each loop iteration, it will update this variable. So usually it's an increment of 1. And so most for loops act like that. They increment the variable by 1. So let's call this column. So we use the keyword let to declare a variable, and column is the name of our iterator. So going back to our picture, what we're trying to do is go from column to column, from left to right. So all this is one column. And so we move from the first column to the second column, to the third column, to the fourth column, like that. So column is from left to right. And we're just going to increase the number from 0 all the way to canvas width. And that's how many columns we're going to draw. And I'm going to initialize this variable, this iterator, to 0. Because remember, on our diagram here, we want to start with the number 0 for the x coordinate for the first column. So let's make that 0. And it's kind of like a statement inside this little for loop. So there's 3 parts to every for loop. So we use a semicolon to separate the parts of the for loop. So this is the declaration part. Now we're going to put the conditional part. So this is a condition that the computer will check on each loop iteration, and if it passes, it'll do the next loop. If it doesn't pass for any reason, it'll stop the loop immediately. So let's have it loop so long as column is less than canvas width. So canvas dot width. And the final part is the update part. So you're going to update the variable that you declared. And I wanted to increase by 1 on each loop iteration. So a shorthand way of doing that is just to say column plus plus. And that means add 1 to column on each time you go around the loop. So column plus plus. And now closing parentheses. So these should be matching parentheses around this whole declaration of the for loop here. And now we're going to put the body of the for loop in. So hit enter and opening curly brace, so left curly brace, and it'll close it for you. And now hit enter. Now we're going to define what happens on each loop. And so what we want to do is to draw a little rectangle on this column number, whatever that may be. So we're going to draw one at wherever column is and inside this loop. So let's copy this, select these 2 lines, and Control C to copy, and now put them in the body of the for loop, Control V. You can right click and click on Format Document, and that'll fix all the tabs and spacing issues from a copy-paste operation like this. So now, instead of drawing it at the middle of the screen, which is canvas width divided by 2, canvas height divided by 2, let's put it at wherever column is. And so we're going to type column here instead. And how high do we want it to be? Well, 0 in the y coordinate meant the top of the screen. So I want to start at the top of the screen. So let's just leave this part 0. And that'll keep everything at the very top. Just to quickly go over this one more time, we declared a for loop and we named an iterator called column. And column is going to go through every single column on the web page, no matter how many that may be. It may be 1920, or it could be even more than that, depending on what the user has for their display settings. And then as long as column is less than canvas width, we're good to go, and we can keep on looping. As soon as column reaches canvas width or goes past or tries to go past, it won't do that, because it'll just stop the loop. We won't be drawing past the right of the screen. So, and then on each loop, column gets updated by adding 1 to it. So column starts out as 0, and then imagine putting a 0 right here because column is 0. And then it goes around the loop and updates column to 1 now. So 0 plus 1 is 1. And now you put a 1 there, and then go around the loop. 1 plus 1 is 2. And so that becomes a 2. So now that should draw a pixel at 0, 1, 2, 3, 4, all the way to the right of the screen. And it should only be 1 row. So a very thin line. We might have to increase the height of these rectangles. Let's increase it to 2 so we can see it. Okay, and so let's go back to our web page and see if we correctly looped over our first row of pixels. And they should be all magenta. They should be all pink, purplish color. All right, look at that. There it is. So we've successfully made our first loop of pixels. And so now it goes from 0, 0, which is this little pixel right here. And then it goes all the way, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to however many this is. And I can't remember on my device. It's not a full 1920 wide, but it's pretty close. So it goes all the way across there, and then it stops when it gets to the end. So that was successful. And now let's put it back to 1 now that we know that it's working. So now it really is just 1 pixel wide and 1 pixel tall for each pixel. So let's go back and check. Yeah, all right, so there it is. So it's very thin now. So you You might have trouble seeing that on the YouTube video, but it is there. Great. So let's go back in now and see if we can loop going downwards now. So let's go back to our image that shows the sample screen coordinates of a 10 by 10 display. And so notice that the Y number gets incremented as we go down the screen. So 0, 1, 2, 3, 4, 5, and so on until the very bottom, which will be called canvas.height. So canvas.height is way down there on the bottom of the screen, and it starts at 0. So let's try to do another loop. Let's copy this. So copy all this code, Control C, Control V, and let's name these something different. So how about row for this iterator? So row equals 0, change column to row, and now we want it to be less than canvas height. So change the width to height. And row plus plus. Now put a 0 here for column because we're not focusing on that right now. We will in a minute, but for now just put a 0. And instead on the second number, which is the Y coordinate, type row. And it will place whatever number row is, it'll place it right there, and that'll update where it draws the rectangle or the little pixel. So again, we want it to be a magenta color, so we just set it to magenta, and then we draw where that row location is. And so now if we look at this code, it starts off as 0, row equals 0. So long as row is less than canvas height, I want you to keep looping, so that's good. And then on every loop, increase row by 1. So row equals row plus 1, or row plus plus. So it's going to be 0, and then 1, and then 2, and then 3, and so forth, all the way until it gets to whatever canvas height is. And that could be 1080 or whatever kind of resolution that you may have on your system. Let's go see now if that went down. It should have gone down the page on the left-hand side. So we should have all the first pixels of every row filled in on the web page. Let's see if that's the case. And again, let's make this a little wider than 1, just so we can see it. So let's make it 2. All right, so with my OBS broadcasting software, it places a yellow line like right here and yellow line right there. So actually my purple line is there, but it's being covered up by my own system right now. So you probably can see it on the video, but just to show you that it's there, I'm gonna restore down. And now we can definitely see, yes, that we went downwards on the web page with every single pixel in this column. So let's change it back to 1 and see if it's still there. Yes, okay, everything's still there, so it's displaying correctly. So that's great, so we're getting there. So now what we need to do is, let's go back to our grid here of numbers. So our final goal is to fill all the pixels of the screen. So what we want to do is go from left to right, top to bottom, just like if you're reading a book. So what we need here in the end is a double loop or a nested loop. And so what we want is the outside loop to go slowly. So the outside loop will go 0, 1, 2, 3, 4, 5, like that. And then the inner loop will go fast. So it'll go 0, like on the left side here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it resets to 0. Meanwhile, the other loop increments 1. So now it's 0, 1, and then it goes through the inner loop again, resets, the outer loop increments 1, and then we go across again. So let's see how to do this in code. So the column loop was the one that went from left to right. It went all the way across the canvas width. So that one needs to be the fast inner loop. So tell you what, let's take out this code. This row loop will be our big outer loop that will get updated more slowly. And inside here, we're going to put the tight little loop that goes across the screen. So let's select all this with the mouse and then Control X to cut, and then click anywhere in here in the body of the for loop and paste. And then right click and format document. Okay, so now we have an outer loop that sets row to 0, and then we have an inner loop that sets column to 0. So remember, on the other loop we had the row variable right here, and so let's erase that 0 and put the variable row. That should do the trick. So let's remove a space by hitting backspace, and then let's add a comment here. So how we do that in JavaScript, remember, is 2 forward slashes. And this will make a comment for our human eyes only, so the computer will skip over this. So loop over all pixels on screen. So let's follow this loop and see if we can make some sense of it, because I know nested loops can be kind of tricky and it's hard to wrap your head around them sometimes, but let's just take it one step at a time. So row is 0 and column is 0. And so now we go down here and column and row are here. So column is first, that's the X coordinate, and that's 0. And row is still 0. So we have 0, 0, which would correspond to the very first pixel of our screen, which is the top left-hand corner, right? So if we go down to our image again, so that's this one right here, 0, 0, or column, row. So column is the first number, and column should increase first. Row should stay 0. So let's see if that's the case. So we go back to our code, and this little loop here runs its full course before this one gets to its next iteration. So we start at column equals 0, and that's 0 in the X coordinate. And then we run all the way to the end of the screen, canvas width. So that's 0, 0 right there where my mouse is, all the way across to canvas width. That's one loop. And it draws a little pixel for every single number, however many that might be. Now, when it gets to this and it fails this check, let's say its column is equal to canvas width. Well, that's not less than canvas width anymore, so this check fails. It pops out of this loop and then returns to this loop, and now row is incremented by 1. So now row is 1, then we hit this loop again, and it gets set back to 0. So column is now 0 again, but row is 1, remember? So fill in those numbers in your mind. So column is 0 again, but row is now 1. And so 1 on the Y coordinate is the very next pixel down. So not the top pixel, but the very next pixel down. So go back to my picture here, it'd be right here, because row is now 1. So now we're going to do that tight inner loop again, the column loop. So column is 0, and then column is going to get updated really quickly and go all the way across the screen again to canvas width. So let's see if that's the case. And yes, that's the case. So here's the column loop. It goes real fast right across the screen. And then when it fails this check once again, it pops out of this loop, goes back to the top, and now row becomes 2. So that moves one row down. And then it enters this tight little loop again and goes across the screen. So it operates much like you would read a book. So it starts with 0, 0, and then goes across, well, it's backwards on my camera. So 0, 0, which is the top left-hand corner, goes across the screen. Then it gets reset to 0 and moves down 1. And so now it's 0, 1. And then it goes across the screen, gets reset, 0, 2, across the screen, 0, 3, like that. So the little inner loop, this little inner loop goes across the screen real fast. And then the outer loop moves more slowly. It's like 2 gears. If you can imagine 2 gears in your mind, a big gear and a little inner gear. The little inner gear is like going really fast and it's going across the screen, but it keeps getting reset. And then the big gear turns every so often. So whenever the little gear gets to the end of its rope, when it gets to the end of the screen, the big gear turns one more cog. And then so you have that dual action going on. So the little one is going really fast, and then the outer one kind of changes more slowly as the little one on the inside gets reset. And so therefore, we should be correctly going across the screen and then getting reset and updating this to 1, and then going across the screen, reset, updating that to 2, across the screen, like that. And that way we follow the pattern that the browser was meant to be laid out in, and most image software operates like this too, that 0, 0 is the top left-hand corner of the coordinate system, and it goes across this way first, and then it goes down, just like you would read a book. In keeping with that pattern and not doing something different or crazy, we're going along with how the memory is laid out, and therefore it will do those operations faster because it reflects how the computer is storing those pixel values in a row. So internally the computer has all these pixels lined up in memory, and so we're accessing them in the same order that the computer is laid out. And so that'll be beneficial for going as fast as possible through these loops. Again, if you have a 1080p display, that's 1920 pixels times 1080 pixels, and that's over 2 million pixels to get through. And you might think that that would take forever, but computers nowadays are so blazingly, mind-numbingly fast that it happens in like a second. So let's go see if that's the case, and let's see if we have successfully filled in all the pixels with a bright magenta color. All right, we did it. So we have every single pixel now filled in with the magenta color. And so it kind of looked like we just did a flood fill of the whole page, but actually we did it the hard way. We did it one little bitty pixel at a time. And so let's refresh this page, and you can see that it takes just a second to get through all those pixels. I'm going to refresh and see it's thinking, bam, there it is. Okay, so let's do it one more time. So you can see the little spinning wheel up here. It's calculating all those positions. So let's do it one more time. Thinking, and done. So it got through millions of pixels in that maybe 1 second. So that's pretty amazing that it can do 2 large loops like that so quickly. So now let's have some fun with these colors, and let's change the color of all the pixels on the screen. So let's change them to blue. And there we go. So millions of blue little tiny pixels. Now you might look at something like this and say, well, I don't know if that's really all the pixels that are being updated. Can't you just cheat and just do like a big rectangle? Well, to prove that it's individual pixels that we're drawing one at a time,
we're going to now change the color of each pixel depending on where it is on the screen. So if it's over on the left side, we're going to change it to maybe like a darker color. And as it gets to the right side, let's change it to brighter and brighter until it's full intensity on the right side. So let's change it to like a red so we can see it real clearly. So it's all the pixels are set to bright red. And to help us do this, let's create a couple of new variables that will hold the X location and the Y location of every pixel. And so let's go above the for loop here and hit enter. And let's create a couple of new variables. So let canvas X equals 0. And I just like initializing my variables. So you don't have to initialize this to 0, but I just like doing that because it tells the browser that this will be a number and not something else like a string. So, and let's do the same for Y. So let canvas Y. And so what we want to do now with these X and Y variables is to turn them into something useful that we can just scale up a color by. So what I mean by that is that instead of having row and column to work with, which might be in the thousands depending on the user's display resolution, we're going to make canvas X and Y both go from 0 to 1. So back on our image here, let's say if we're going across the screen this way, and we're just going to take a look at the X coordinate now. So 0, 1, 2, 3, and so on. And what we can do is just divide that number by how many pixels there are. So in this one, I'm just going to physically count them because I can do that on this small resolution. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I count 10 pixels total. And so we want to turn this first number into a percentage or a fraction of that. And so all you do is take this X coordinate, whatever it might be, so 0 in this case, and divide it by how many pixels you have. So I had 10 pixels, so we take 0 and divide by 10. And then we do that for this, 1 divided by 10, 2 divided by 10, 3 divided by 10, 4 divided by 10, and so on, all the way till we get to 9 divided by 10. And so that'll give us a percentage from 0 to 1. Now, you may have noticed that this doesn't quite work. If I do 9 divided by 10, that's 0.9. So that doesn't quite equal 1. So we want exactly 1 at the end. So what we're going to do is just subtract 1 off the number of pixels and then use that as the denominator. So we have 10 pixels, and what's 10 pixels minus 1? So 10 minus 1 is 9. So we'll divide everything by 9. So this will be 0 divided by 9, 1 divided by 9, 2 divided by 9, 3 divided by 9, 4, 5, 6, 7, 8 divided by 9, and then finally 9 divided by 9, which is truly 1, and it's exactly 1. So we have exactly 0 to 1.0. And so that'll give us a nice gradation from 0 to 1 that reflects where the pixel is located on the screen. Is it on the left side or is it on the right side? Or is it somewhere in the middle? So let's try that now with the X coordinate and see if we can get that working. So I'm going to use this canvas X that I just declared. And inside the tight little loop, the inner loop, let's set canvas X equals, and then whatever column is, remember a column goes from left to right. So 0 to however many pixels you have. So column divided by how many pixels do you have? Well, we set the number of pixels ourselves, right here, we said canvas width was whatever window inner width is. And we, ahead of time, we don't know what that is. It could be in the thousands. It could be a 900 something. It could be, you know, a 4K display. We don't know. So we're just going to divide that by whatever the canvas width happens to be. So canvas dot width. And I'm going to leave the subtraction of 1 off for now, just so we can see that this is working in the browser console. So and let's go ahead and print this out in the browser console, and we'll check it out and see if it's working how we expect. So how we do that in JavaScript is type console.log. And it's a function, so it takes parentheses, and then you put in quotes what you want the output to be, and then you can also put variable names in there. Let's put quotes first, and we'll say canvas x is space, and then we're going to use string concatenation. Remember that from the JavaScript episode? So you can take 2 strings and mash them together. So we're going to do plus, and that's how you do string concatenation. And then your variable name, so canvas x. And whatever canvas x is, it'll just put it right there in your sentence. So it'll say canvas x is 0, canvas x is 0.01, or whatever it may be at that moment. So type canvas x, and it'll retrieve that value. And now that's a statement, so we end that with a semicolon. Okay. Oh, and I forgot one thing, that actually this will happen for every single pixel. And so I want to just test the very first row of straight across from left to right. So let's do a condition here. So if statement, and put parentheses, and now only when row equals 0, like for the very first row at the top of the screen, do we want to do this, just to print out this debug information. So if row equals, and remember to check for equality, use the double equals. So row double equals 0. Let's hit enter and put a pair of curly braces, so left curly brace, and it'll close it up for you. Hit enter, and now cut and paste this line, so console log. Let's put that inside there. Control X, Control V. Okay. So now it'll only do that on the first row. We don't want to print it out for every single row. That'll be too much output in the console. So let's go check our console now. And how we check the browser console, remember, is right-click, inspect. Okay, and then click on console. If you don't see it right away, you might have to hit refresh. Sometimes the live server fails to refresh the HTML document after it's been sitting there for a while. So while I was sitting there talking about pixels and locations of screen coordinates, it kind of fell asleep on me. So, but now we can see that it looks like it's working. So let's go. This is a really long list. You have to scroll. See this little scroll bar? Scroll all the way, because it did this for about 1,000 times. Okay, so canvas X is 0. That's right here. And then a little above 0, so that's the very next one. And then it keeps incrementing. So let's scroll down. Now it's 0.1, so that's about over here. And then it should get to 0.2, that's about here. Keep scrolling, 0.3. I'm going to scroll down a little faster. 0.4. Now at this point, when it's 0.5 exactly, right here, this line, that's when it's in the middle of the window. So that's helpful. And we keep going, 0.6, 0.7, 0.8, 0.9. Now it should not go past 1. So the last value is indeed 0.9992. So that's the very last pixel right here. So actually, we want this last value to be a pure 1, so 1.0. And so how we can accomplish that is just by taking off 1 off the number of pixels in the denominator. So let's go do that. So remember on our diagram here, we had 10 pixels and we had to take 1 off those 10 pixels. So 10 minus 1 equals 9. And then we could divide all these numbers by 9. And when we got to the last one, 9 divided by 9 is indeed 1. So we're going to do that with this loop now. So canvas width right now is 1 number too high. So we're going to, let's select it and type the parentheses, and that'll put parentheses around it. And let's do a space -1. So now that'll just take off 1 little number off of canvas. So instead of 1920, it'll be 1919. And so because let's say if you're doing that many pixels, remember it starts at 0. So that would go from 0 to 1919. And so when you divide 1919 by 1919, which is 1 less than canvas width, then you indeed get a pure 1.0. So let's go in the browser now and see if that's the case. And there it is. That's the end of the list. So canvas X is 1. So that's that very last pixel right here. And I only had it do this first row. So all these numbers are for this very first row, or the first sentence in your book. So it goes all the way like this, and it stops there. And that's where I had it stop. Now I could have let it go all the way down, but that would have taken forever because it has to print out all these numbers, and that takes time. Even though it does it really fast, but it takes extra time. And we just wanted to see if it was working, so it's working now. And so now we can select this and Control /, and that'll comment that out. And so we know it's working now. Now let's do the same for the Y coordinate. So go to the end of this line and hit enter, and do the same for canvas Y. So canvas Y equals, now with the canvas Y, we have to use the row variable instead of the column variable. So type row divided by, and now instead of canvas width -1, it's canvas height -1. So parentheses, canvas dot height -1. And that will make it evenly divisible so we get 1 at the end of the loop. So now hit or type a semicolon at the end of the line because that's a statement. And so let's just do a quick check of this. And what we're going to do is take this console log here, copy that, and then go right past this right curly brace here and hit enter. So you're below the little inner loop, and then paste that in there and change this to Y. So Y and Y. Now on every iteration at the beginning of each row, so that means this one is the beginning, and then it won't loop again until it gets to this one, then it prints out again, then it won't loop until it gets to the next one. So it'll print for all these pixels what the canvas Y coordinate is. So it should divide evenly. By the time we get to the bottom of the screen, canvas Y should be an even 1. So let's go see if that's the case. All right, and there it is. So canvas Y is 1. So it went all the way down this way. And if you go back up to the very top, it should be canvas Y equals 0. There it is, yeah. So it increments just a little bit every time. 0.1, 0.2, 0.3, 0.4, 0.5, and then 1. Now it got through this really quickly because if you notice, we don't have a lot of height here because I took up most of it with my output window. But if we do this and run it again, now let's inspect. So now it should be much longer. Yeah. So it's in the 800ths or something like that. So it goes much more slowly now, but it does increment. So 0.1, 0.2, 0.3, and then I'm just going to skip ahead all the way down to the bottom, and then 0.999 or 998, and then finally we get to 1. So that's perfect. So now we can use this as a percentage scaling factor to multiply by the red color. And so if we multiply, like if we were starting over here, let's say, we would multiply that by the X value. So that's 0. So red would be 0 here, and you would get just a black pixel. So no color at all. And then when it got to 0.1, that's like a really dark red. And then 0.2, a little brighter, 0.3, a little brighter, and then 0.5 is medium red color. And then 0.7, 0.8 is getting brighter and brighter. And then finally, we get full intensity when we get to the right of the screen, which is 1.0 times the red intensity. So now let's go back and comment this out so it doesn't print to the console log anymore. We don't need that. We know it's working. And in order to make a gradation of color, we can't use the keyword red anymore because that just means full intensity red. So now we actually have to use an RGB value to specify what the color should be for that pixel. So now let's create a couple of new variables. So let R equals 0, and that's going to stand for the red channel. Let G equals 0, and let B equals 0. So those little variable names stand for red, green, and blue. Now, if you've been following along with this series since chapter 0, we did this before where we created a string from scratch that had the RGB values inside of it. And then we took that string and gave it to this property right here, fill style. So we're going to build up a string component-wise that denotes what the R, G, and B should be for this particular pixel. Let's keep the quotes there, but erase the word red. And now the final form should look like this, RGB. And in fact, let's just put this in first to make sure that it's working how we expect. So RGB 255, 0, 0, parentheses. So that's a string and has the letters RGB and then the values for those. So 255 is the max value and 0 is the smallest value you can have. And they're integers, so no fractions or decimals or anything like that. So 255 means maximum intensity. And so this should be a bright red for the whole screen. So nothing should have changed actually. It should just remain red. So let's go check our web page, make sure. Yes. Okay, so it's still all red. And just to prove that that's working, let's change it to yellow. So I'm going to make the green channel full intensity also. So now we have 255, 255, 0. And there we go. There's our yellow. So it's working as expected. That's too bright for my eyes though. So let's change it back to red. So now what we're going to do is use the string concatenation method again and build up this string from scratch and then stick in those little RGB values. So to get started with this, let's make the red channel full intensity. So R equals 255. And then we're going to build up a string component-wise out of little pieces And when it comes time to put this value in, we're going to stick an R right in that spot. So let's build this string up now. Let's erase all that. And now it starts off with a string. So type double quotes and type RGB opening parentheses, but stop there. And now go past the closing quote and put a space, and now do plus symbol. And that's how you do string concatenation in JavaScript. Remember, you use the plus symbol and it sticks two strings together. So now we can put even though this is not technically a string, it's a number, we can stick that variable right there and it'll turn it into a string and smash it together with the other string. And so it'll all read as one phrase. So let's put the R right there. And now let's continue on with our phrase that we want. So we need RGB and then a value, comma, another value, comma, another value, and then a closing parenthesis to finish it out. So let's do the plus symbol again. And now we need a comma. So remember the full quote was RGB 255 or R, comma, and then G, comma, B. And then we wanted a parentheses. So that's our target goal for this phrase that we're building up component-wise. So now what comes next? So I got the R right here. And what comes next? So a comma. And so that is literally just one character. So we still need quotes though. So quotes, and then put a comma. And so that covers this comma right here. And now we need the G variable. So do the plus again, G, plus. Now what comes next? Another comma. So just like we did for this one, we need quotes and then put a little comma in there, and that's all you need to do. And then finally, the B comes. So plus B, and then plus, and now we're not quite done. We need one more little thing here, which is the closing parenthesis. And that's part of a string, so remember we need quotes again. So quotes, closing parenthesis. And now we're finally done with this phrase build up. So we have RGB, opening parenthesis, and then we stick in the R, we stick a comma, G goes to the next, and then comma, and then B goes next, and then finally a parenthesis to close it out. Let's comment that out with a couple of forward slashes. Okay, so now R is 255, so when it comes time to fill this into the string, which will fill the rectangle with that color, it'll make R 255, and then it'll put in whatever G and B are. So G and B are currently 0. We haven't done anything with those. So it should be 255, 0, 0 for every single pixel. Let's go back to our web page and see if that's the case. All right, we're doing really good here. So we're doing exactly what we need to do. So now let's try to mess around with the RGB values and see if we can get some different colors for the pixels. So now let's set G to 255 and B, let's leave it at 0. And we should get full intensity red and full intensity green is a bright yellow. So let's see if that's the case. Cool. All right. And if we make all the channels bright, it should be a pure white. There it is. And if we take off a 5 off of each channel, we should get a dark gray color. There it is. Okay, so we have a dark gray color, almost black, but not quite. So now that we have this in place and we can put in whatever values we want just by changing these little numbers here, we can actually create some little functions that go right here and that produce different values depending on where the pixel is located. So now let's turn all the G and B's to 0. And let's make red. How about we use the canvas X? So canvas X goes from, I'm going to make a comment here. Canvas X goes from 0.0 to 1.0. So let's try this. We're going to use the canvas X as a scaling factor. So from 0 to full intensity, which is 1. And we're going to multiply that by 255. And so here's what that looks like. Canvas X times 255. And so if canvas X is 0 and it's way over on the left side, this is going to be 0. 0 times anything is 0. But if it's like 0.1, if it's over here somewhere, it's going to be 25.5, let's say. And so that's going to be a really dark red. And then by the time we get to the middle here, 0.5 times this is 120 something. So that'll be like a medium red. And then when it gets over to the right side of the screen, it's going to be a 1.0. And 1 times 255 is itself 255, and that's the maximum. So it should go from a really dark, like black color, all the way through a dark red, medium red, bright red, to full intensity red by the time we get across to the right side of the screen. So now there's one more thing we need to do though, before we go and check on that. And the Canvas system likes pure integer numbers. It doesn't like decimal numbers for its colors. So you shouldn't have a fractional part on your numbers when you specify the R, G, and B channels. They should be just whole integers. So let's do this with the R channel now. R equals, so we're going to use a math function. So call the math object, which is kind of like a math library. And then we're going to use the floor function, which will round the number down to the next whole integer. So it essentially removes any fractional part that might be past the decimal place. So it is a function, so it needs parentheses, and then you put in the number that you want to operate on. And so we want to operate on the R itself, so just type R again. So let's say it was 100.67254 or something like that. It would take off the 0.67254 and then leave you with 100, and then cuts off the fractional part. So you're left with a nice whole integer number that the Canvas system likes working with. Okay, so now let's go look at our, we should have a nice gradient now from dark to bright red. So let's go check it out. Wow, isn't that cool? So it starts here, and all the columns, each column, as it goes from left to right, starts out at 0 in intensity, and then it ramps up all the way to get to the end, and it's full intensity here at 255, because we multiplied it by where it is on the web page. So 0.0, and then 0.5 is in the middle, and then 1.0 times 255. So now that we have this working, let's have some fun with these numbers. Let's see if we can get some different patterns with our canvas colors. So let's say if we wanted to reverse it, so have it be full intensity on the left side of the web page to 0 intensity on the right side, so opposite of what we just did. All you need to do in that case is subtract canvas from 1. So put that in parentheses, and then before canvas X type 1 minus. And that will flip whatever canvas is. So if canvas is 0, 1 minus 0 is 1. And if canvas is 1, then 1 minus 1 is 0. So it just flips everything around. And so now if we go back and look at our web page, see we have full intensity. So when the X is 0, then it's full intensity. And when X is the full value of the canvas width, then it's 0 intensity. So we just flipped it around. So let's put that back. And now let's do something similar for the green and blue channels as well. So erase the 0 here, and let's do canvas Y for the green. So canvas Y times 255. And again, that'll get you a number with a fractional component, and we don't want any fractional components, so we want pure integer numbers. So how we do that is to floor the number down. So G equals math object dot floor, which is a function, and you put the G itself inside the function. And just so we can see the effects on the green channel alone, let's put the red channel back to 0. So R equals 0. And now we'll just see the green channel change as it goes down the web page. So let's go see that. That's pretty cool. So we have a black beginning for our first row here, and then as it gets down to each row is subsequently more bright than the last row. And so when you get down to the bottom, it's full intensity green. So 1.0 times 255 is 255. And then this one up here is 0 times 255, which is 0. And now let's take out this R equals 0, and it should have a nice gradient from black in the left-hand top corner to a yellow on the bottom right-hand corner, because you'll have 0 in the red and green channels, which will be black, but by the time you get to the bottom right-hand corner, both of those will be 255, and that's a bright yellow. So it'll be 255, 255, 0 by the time you get to the right bottom corner. So let's see if that's the case when we erase this R equals 0. Cool. So we have really dark colors over here. So it starts off with no color at all, black, and then it subsequently adds a little bit on each pixel as it goes to the right. It adds more and more red. And then each pixel as it goes downward, it adds more green to it. And then if you follow it this way, it goes through a dark orange, brownish color, and then it finally gets to where they're both full intensity, and that's a pure yellow color. So the red is all the way over to the right, and that's where this one is. And the green, when it gets down here, is full intensity when it gets down to the bottom. And so it's also full intensity green at the bottom. For fun, let's just try that with the blue channel as well. So erase the B equals 0. And let's do, how about 1 minus canvas X? So parentheses, and then 1 minus canvas X. Just to be different. And then times that by the possibilities of color intensities, so 255. And again, that'll produce a number with a fractional component, so we want to lop off that fractional component, and we do that with the floor function. So B equals math.floor function, and that takes the number that you want to remove the fractional component, and that's B itself. So now let's take a look at the result. Ooh, I like that. So now we have a full intensity blue, because remember we said that the blue was going to be 1 minus canvas X. So if canvas X is 0 up in this left-hand corner, then 1 minus 0 is 1. So it's going to be full intensity blue to no intensity blue as you go from left to right. And that's what we get. And then we get this cool magenta purple color in the middle here. So I really like this look. I think we'll leave it like this for when we put it up on GitHub later. Oh, let's change this text output. So right now it's reading hello from the JS file. Let's say how many pixels it has processed. That'll be a helpful message for the user. So go back to where it says hello from the JS file. Now, one thing we need to do though, before we update that, is take these two lines and Control X to cut them, move these lines back up, and now paste them underneath the canvas width and height, because we're going to need those values in the output. So now you can erase the text that says hello from the JS file. And let's put instead, let's first print out the canvas width. So canvas width, colon, space, and then let's do our string concatenation method. So that is using a plus sign operator, and then put the canvas width variable in there. So canvas.width plus again, and now we're going to print out canvas height equals, and then whatever canvas height is. So let's do that in the same manner. So canvas height, I'll just put H, and that means height, and then in colon, space, and now plus canvas height, canvas dot height, plus, and here's a little trick that is handy. Let's say if you want to go on to the next line and print something on the second line, you don't want to have all your text in one line completely across the screen. You want to do multiple lines of text. You can insert a line break tag wherever you want to break to the next line. So that's done by putting quotes and then left angle bracket or shift less than sign, and then BR, and then right angle bracket or greater than sign. And now go past the quotes and do plus. And now, even though this is giving an error right now, see this little red mark, it's saying we need some more information here. Go ahead and hit enter on the next line. And this will remind us that we're printing this on the next line. And so now we put quotes and total pixels, total pixel count. How about that? Colon, and then go past the quotation again and use the addition operator to concatenate these strings together. And let's do the total resolution of the image. So that equals the width times the height. So let's put that all in parentheses so it gets done as one unit. Inside the parentheses, just type canvas dot width times canvas dot height. And that should give us the total pixel count that it had to go through to generate this image. Okay, so let's go see how that looks on our web page now and see if the line break is working. All right, cool. So, I forgot a space here. So we should add one little space before this C of canvas H. So let's go do that. Canvas H. So it needs a little space right here because JavaScript doesn't know where you want the spaces. So it just kind of it mashes them all together, and it doesn't put spaces in there for you unless you specifically add a space to the phrase. So now it should be appearing correctly. Okay, that looks better. So now canvas width is 1280 on my machine. Now I'm on a laptop, and because I'm running OBS software in the background, I decreased the resolution a little bit so that my frame rate is still 60 FPS on most of the apps that we'll be using. So, and for the video purposes, I want the frame rate to be 60 FPS. So when I upload this to YouTube, it'll be nice and smooth. So my resolution isn't a full HD like it normally is. So this is only 1280 across by 652 up and down. So if you multiply all those together, you get 834,560. That's still quite a big number. That's fairly close to 1 million pixels. So you can imagine if you had a full 1920 by 1080, you would have this number would be in the 2 millions or higher. And so possibly when you run this on your own device, if you're on a desktop or a laptop that has full HD resolution, then you will see much larger numbers down here. And so even though it takes, like if I refresh this, it takes about 2 seconds. So even though it takes a couple of seconds to generate this image and go through all those pixels, that still is pretty amazing that it's going through that loop 834,000 times, and it's setting all those little rectangles, all the little pixels to whatever color we want. So I still think that's amazing, even though it's going not at real-time rates, but it is just a couple seconds to calculate all that. And so since we've made these RGB channels as variables, we can do whatever we like inside these loops and set them to whatever we want and generate countless varieties of patterns and colors just by having these as variables. So my challenge to you all is to take these RGB channels and just mess around with the little calculations for each channel and see what kind of patterns you can come up with. So just have fun with it. And that's the best way to learn, is just by taking those variables and trying out different numbers and different algorithms and seeing what works and seeing what doesn't and seeing what patterns you can come up with. And you can learn really quickly that way. And I've made a lot of discoveries just by messing around with variables like that and having something unexpected happen, but then that taught me about more about the system, and then I was able to use that knowledge from that random occurrence or that mistake or that random pattern that happened, and I was able to use that later on when I needed it in future projects. Okay, so the last thing I want to do today is upload our new demo and our new project up to our repository on GitHub. So as you recall, VS Code makes this super simple. And so let's go inside VS Code. And if everything went correctly on your machine, and if you have Git installed, as we did on the episode about Git and GitHub, you should have 3 notifications and then 3 U's here, because we've created 3 new files. And they're currently untracked, but we're about to remedy that. And so we're going to upload our changes now to our GitHub repositories. And so, and before we push these changes to our GitHub repositories, let's go in the README file and add a link to the demo so that people online who visit our repositories can try out this new demo that loops over all the pixels. So let's scroll down to the bottom here where it says live demos. And just take this whole thing, this last bullet point here, which begins with the asterisk, and select these lines here and copy and just paste them below. And we're going to change them in a moment. So instead of randomized colors, now this text will appear as the link. So that's what people will see when they go to click on it. So how about let's call pixel loop. And we have to change the HTML file from random colors to whatever we named the demo. So that's pixelloop.html. And the loop has a capital L. So pixelloop.html. And then the description, we can change that to something like loops over each and every pixel on the screen and sets that pixel to a unique RGB color. Okay, so now we should have 4 notifications over here, which means 4 files have changed. And so this one says M, if you notice here, so that means modified. So that one was currently being tracked, and that's why it doesn't say the U there. It says M for modified. But these say U because we haven't uploaded those yet, and we haven't started tracking them. But as soon as we upload these changes to GitHub in a moment, then all those U's should go away, and these green colors will go away too. And then it'll just keep track of all the files that we have in our RayTracing projects main folder here. So now we can go to the source control icon over here that has the 4 beside it. Click on there. And now it has all the files that have changed. So pixelloop.html, the README has changed, RayTracing styles, and pixelloop.js. And it shows that these are 3 new files, and then this one is an old file that has been modified. So let's enter a message that describes what this commit is doing. And so we'll say something like added new pixel loop demo. Okay, and now we hit the purple button, commit. And now my favorite part is you just hit this sync changes button, and that immediately syncs all your changes that you've made here on your local machine up to the cloud on GitHub. And that way when you go to your repository, or whoever visits your repository online, they can see those changes as well immediately. So click on Sync Changes. And just like that, it's done. I just love that feature. So now let's go check that out online. Let's go to our repository. So I named mine RayTracing projects, and so you might have a similar name for yours as well. And let's refresh the page. And look at there, it says added new pixel loop demo. So now let's scroll down. We have our beautiful image here. And there it is, it's at the very bottom. So the latest demo is at the bottom here, and it's under the live demos section. And it says loops over each and every pixel on the screen and sets that pixel to a unique RGB color. So let's go ahead and try that. I'm going to open it up in a new tab. So right click and then open in a new tab. And there it is. So now it lives on our repository on GitHub, and all the people that visit your repository here can see your new demo. And so if you want to, and if they want to look at the source code, they can go to Pixel Loop. And here's the little HTML shell that we had coded first. And then inside the CSS folder, we have our RayTracing styles. This is our new cascading style sheet, and that defines the styles. And then the heart of the program is in the JS file. So that's pixelloop.js. And then they can see how you did it with the double loop here with the outside row loop and the inside column loop. Well, all right. I hope you enjoyed that. Looping over all the pixels on the screen and setting them to various colors and patterns. So again, the big takeaway from today's episode is that if you can just put one pixel on the screen and then use that knowledge to loop over all the pixels on the screen and set them to whatever color you want, then you're able to start writing a sophisticated ray tracer on top of that foundation. And so now that we have the ability to loop over all the pixels on the screen and set them to whatever color we like, we can move on to creating a ray for each of those pixels and then have the ray go out into the scene and interact with the objects in the scene and then report back a color for that individual pixel. And pixel by pixel, we can build up our final ray traced image. So on the next episode, we're going to take a look at how to construct a ray. And in order to understand how rays are defined and how they work inside of a ray tracer, we need to take a look at vectors. And if you haven't worked with vectors before, don't worry. As with all aspects of this video series, I want to present things in the simplest way. And whenever we come across a new topic, I want to start from scratch and show how it's built up. So much like we did for our source code files today, we'll start with a blank slate and then we'll take a look at just some basics of vectors and how we can use those vectors to accomplish the ray tracing tasks that we want to do in the browser. And so I'm really excited to show you that on the next episode. And so I'll see you next time.